Imagine waking up on Mars, real Mars, not a research station in a pressurized habitat, not a temporary outpost, a real city, with blue skies, with rain, with breathable air. It sounds like science fiction, like something from a novel written 50 years ago. But there are serious scientists, serious engineers, and serious thinkers who believe it's possible. Not tomorrow, not in 50 years, but centuries from now. Maybe we terraform Mars. Maybe we transform it from a barren, frozen wasteland into a living world. What would it take? What's the engineering? What's the timeline? What are the obstacles? And most importantly, should we even try? This is one of the most ambitious ideas humanity has ever conceived. We're not just talking about visiting another planet, we're talking about fundamentally transforming it, changing its atmosphere, warming its climate, creating oceans, seeding life, building a new Earth from scratch. The audacity is staggering. But the science behind it, surprisingly grounded. Welcome to the world of terraforming. Let me show you what it would take to make another planet habitable. First, let's understand what terraforming actually means. The term comes from terra, meaning earth or land. Terraforming means making something Earth-like, making it capable of supporting Earth life, making it habitable for humans without needing spacesuits or artificial environments. This is different from colonization. Colonization is building habitats on an inhospitable world. You create artificial environments. You maintain them. You live inside them. Humans live on the moon in this way, in science fiction, in sealed habitats, completely dependent on technology to survive. Terraforming is different. It's making the world itself hospitable. It's changing the planet so that humans can walk outside, breathe the air, drink from streams, grow crops in soil. It's making a second Earth. The concept is beautiful. It's also extremely ambitious, and it might actually be possible, at least in theory. Let's start with Mars because that's where most terraforming discussion focuses. Mars is the closest habitable analog to Earth in our solar system. It's not easy to make habitable, but compared to Venus or Mercury or the outer planet moons, Mars is almost reasonable. Here's what Mars is like now. The temperature averages minus 65 degrees Celsius. That's minus 85 Fahrenheit. Bone-chillingly cold. The atmospheric pressure is less than 1% of Earth's. You die instantly if exposed to the Martian atmosphere. The air is almost entirely carbon dioxide. It's incredibly thin. It's like standing on Mount Everest, except much worse. The soil is dusty, oxidized, iron-rich rust. It's not great for growing plants. There's water ice beneath the surface, especially near the poles, and there's ice in the polar caps. But liquid water is rare on the surface. The radiation is intense because there's no magnetic field to protect the surface. Solar wind batters Mars directly. So here's what you'd need to do to make Mars habitable. First, you need to warm it up. The average temperature needs to rise by 50 to 100 degrees Celsius. Maybe more. You need liquid water on the surface. You need a thicker atmosphere. You need oxygen, or at least a breathable air mix. You need to deal with the radiation. You need soil that can grow plants. Let's talk about warming Mars first. This is often called the greenhouse warming phase of terraforming. Mars has all the chemical ingredients for a greenhouse atmosphere. It has carbon dioxide in the atmosphere and likely more in the soil, frozen in the regolith. It has other greenhouse gases, methane, water vapor, various industrial compounds. The problem is Mars is cold, really cold. The greenhouse effect isn't strong enough to warm it significantly with the current atmospheric composition. But what if you increase the greenhouse gas concentration? What if you released huge amounts of carbon dioxide into the atmosphere? What if you also added methane, chlorofluorocarbons, methylchloroform, industrial chemicals that are powerful greenhouse gases? Here's an idea some scientists have proposed. Use factories or automated systems to produce massive amounts of these gases. Deploy them all over Mars. Over centuries, these gases would accumulate in the atmosphere. The greenhouse effect would strengthen. Mars would warm. This would take an incredibly long time, centuries, maybe thousands of years. But over those timescales, the temperature would gradually increase. Enough to start melting the polar ice caps, to start releasing more carbon dioxide that's frozen in the soil, to create a runaway greenhouse effect. Once you have some warming, things start happening. Ice melts. Water vapor enters the atmosphere. Water vapor is itself a greenhouse gas. It traps more heat. Things warm up more. More ice melts. You get positive feedback. The process accelerates. Eventually, you've got temperatures where liquid water can exist, where the ice caps have partially melted, where there are liquid water flows, streams, lakes, maybe eventually oceans in the low areas. This is the key to Mars. The southern hemisphere has vast basins. If you melt enough ice, if you add enough water, those basins would fill with water. Mars would have oceans again. Here's the fascinating part. Mars probably had liquid water once. Billions of years ago, it had a thicker atmosphere, higher temperatures, and oceans on the surface. The evidence is everywhere. You can see ancient river channels, delta formations, clearly indicating flowing water. But Mars lost its magnetic field. The solar wind stripped away the atmosphere. The planet cooled and dried. Terraforming Mars would be recreating what Mars once was, restoring it to a more habitable state. But let's talk about the actual timescales, because this is where terraforming gets really ambitious. We're talking about transformations that would take centuries or millennia. Some scientists have calculated that if you completely covered Mars with black absorbing material to maximize heat absorption, you could warm it in about a century. But that's unrealistic. You're not going to cover an entire planet. More realistic scenarios suggest millennia, thousands of years, maybe 5,000 years to achieve a fully terraformed Mars where you could walk outside without a spacesuit. Maybe 10,000 years to have genuinely comfortable conditions. Maybe even longer if you're being conservative. This is the timescale we're talking about. Not centuries in most cases. Not the 200-year timescales you see in science fiction novels. Thousands of years. Multiple millennia. But here's the thing. If you're thinking long-term about human civilization, thousands of years isn't actually that long. Civilizations last for thousands of years. Technology advances dramatically over thousands of years. It's an ambitious project, but it's not impossible. Now, how do you actually do this warming? What are the methods? One proposal is orbital mirrors. You place giant mirrors in space orbiting Mars. These mirrors redirect sunlight toward the Martian surface. They concentrate solar radiation. They warm the planet. This would take enormous mirrors. We're talking about mirrors kilometers in diameter, but in principle, it's possible. The mirrors would need maintenance. They'd need to be adjusted as Mars changes. But over time, they could add significant warming. Another proposal is to release greenhouse gases directly. You could build factories on Mars that produce CFCs or methane or other greenhouse gases. These factories would run for centuries, gradually filling the atmosphere with gases that trap heat. Another idea is to impact Mars with asteroids or comets. You redirect a small asteroid to hit Mars. The impact releases energy. It heats the atmosphere. The asteroid itself might add material. This would be a dramatic but effective way to add energy. However, controlling this is extremely difficult. Impacts are unpredictable. You could miss your target. You could impact the wrong place. Another proposal is to use nuclear weapons. Detonate nuclear weapons in the atmosphere to release energy and produce greenhouse gases. This is controversial both scientifically and ethically, but it's been seriously proposed. The advantage is you could release enormous amounts of energy quickly. The disadvantage is you're basically nuking an entire planet. There are also biological approaches. You could seed Mars with extremophile bacteria, organisms that thrive in harsh conditions. These bacteria would survive in the Martian soil even before terraforming. They'd slowly build up and start processing the environment. They'd release gases. They'd slowly transform the chemistry of the soil. Over thousands of years, they'd contribute to making the planet more habitable. This is interesting because it's not about brute force engineering, it's about biology, about letting life do the work slowly. You could combine all these approaches, use orbital mirrors to add heat, release greenhouse gases to increase the warming effect, deploy bacteria to start processing the soil, impact the planet with asteroids to add water and energy, use nuclear power to run factories. Over thousands of years, these methods working together would gradually transform Mars. The process would have stages. First, you'd warm it enough that ice starts melting at the poles. You'd get liquid water flowing. You'd get an atmosphere that's still mostly carbon dioxide, but thicker. Pressure would be higher. Then, as temperatures increased, you'd thaw more ice. More water vapor would enter the atmosphere. More greenhouse warming. The process would accelerate. Eventually, you'd have temperatures where humans could survive outside with just oxygen masks. The air pressure would be high enough that your blood wouldn't boil. You'd need to breathe bottled oxygen, but you could be outside. Eventually, you'd warm the planet enough and thicken the atmosphere enough that the greenhouse gas could be reduced. You'd stop adding greenhouse gases. You'd start converting carbon dioxide into oxygen. You'd seed plants, lichens, algae. These organisms would photosynthesize. They'd take carbon dioxide and produce oxygen. Over thousands of years, the atmosphere would gradually shift from mostly carbon dioxide to a breathable mix with nitrogen and oxygen. This is the biosphere engineering stage. Life itself becomes the terraforming agent. Microbes, then plants, then more complex ecosystems gradually transform the planet. Eventually, and we're talking about tens of thousands of years from start to finish, Mars would have blue skies, breathable air, liquid water, soil capable of growing plants, temperature in ranges where humans could live comfortably. It would be a new Earth, a sister world. This is the vision. This is what terraforming Mars would eventually look like. But Venus is a different story. Much harder. Venus is a nightmare world. The surface temperature is 462 degrees Celsius. That's 864 Fahrenheit. It's hot enough to melt lead. The atmospheric pressure is 92 times Earth's. It's like being under 900 meters of ocean. The clouds are made of sulfuric acid. The atmosphere is almost entirely carbon dioxide, with clouds of sulfuric acid and other toxic compounds. Venus was once possibly habitable. It might have had liquid water oceans, but a runaway greenhouse effect transformed it into hell. The water evaporated. The hydrogen escaped to space. The atmosphere became a thick, toxic, super hot pressure cooker. Terraforming Venus is possible in theory, but it's far more difficult than Mars. First, you'd need to cool it. Enormously, you'd need to drop the temperature by 400 degrees Celsius. That's extreme. Just stopping the greenhouse warming wouldn't be enough. You'd need to actively cool the planet. One proposal is to place giant sunshades in space between Venus and the Sun. You'd block some of the Sun's radiation. This would reduce heating. It would allow Venus to cool, but you'd need enormous sunshades. And you'd need to maintain them for millennia while the planet gradually cools. You'd also need to deal with the sulfuric acid clouds. These clouds reflect sunlight, which actually helps cool Venus. But they're toxic. They'd need to be dealt with at some point. You'd need to remove the sulfuric acid from the atmosphere, convert it to other compounds. This is chemically feasible, but logistically nightmarish. You'd need to remove a huge amount of carbon dioxide. The atmosphere is so thick that even if you removed half of it, it would still be far thicker than Earth's. You'd need to convert it to other compounds or somehow remove it entirely. One idea is to use microbes that can process carbon dioxide, or chemical reactions that convert carbon dioxide into carbonate rocks that settle out. But here's the key. Venus is so harsh that doing anything there is monumentally difficult. The temperature would destroy robots. The pressure would crush equipment. The sulfuric acid would corrode everything. You couldn't maintain equipment on Venus easily. You'd need incredibly robust systems. Some scientists have proposed floating habitats in the upper atmosphere of Venus. At high altitudes, the temperature and pressure are more moderate. It's warmer than a hot Earth day, but not impossible. It's more manageable than the surface. You could build floating cities in the Venus atmosphere before you ever terraform the surface. But terraforming the entire planet? That's an ambitious project for tens of thousands of years in the future, if ever. Let me tell you about Europa and other moons, because those are interesting too. Europa is a moon of Jupiter. It's covered in ice. Beneath the ice, there's an ocean, a liquid water ocean. Europa is one of the most interesting places in the solar system for this reason. You couldn't terraform Europa in the traditional sense. The ice layer is kilometers thick. The pressure is enormous. You couldn't make the surface habitable because it's permanently frozen. It's far too cold. The sun is too distant. But Europa's ocean is tantalizing. It contains more liquid water than all of Earth's oceans combined. Water is the key ingredient for life as we know it. If there's liquid water, there could be life. Some scientists have proposed melting through the ice and exploring the ocean, creating habitats in the ocean. This wouldn't be terraforming exactly. It would be more like creating underwater habitats. But you could imagine, in the very distant future, artificially warming Europa, using orbital mirrors or other methods to warm the surface and subsurface. Over thousands of years, you could warm it enough to start melting the ice from the inside. You could gradually create a liquid water ocean accessible from the surface. This would be another form of terraforming, not making a planet like Earth, but making it habitable for life, for human habitats, for exploration. Enceladus, another moon of Saturn, has similar characteristics. It's icy. It has an ocean beneath. It could theoretically be warmed and eventually have a more accessible ocean. Titan, Saturn's largest moon, is actually fascinating for terraforming. Titan has a thick atmosphere. It has liquid methane and ethane oceans. It's extremely cold, but it has complex chemistry. Some scientists have speculated that if you warm Titan enough, Increase the temperature by just a few dozen degrees. You could potentially make it habitable for life as we might understand it, even if that life is different from Earth life. Titan could be more easily terraformed than Mars in some ways because it already has an atmosphere. You'd need to warm it and add different gases, but you wouldn't start from zero like you would on Mars. But let's go back to Mars, because that's the most realistic terraforming target for the next few centuries of human civilization. Here's something important. We don't actually know if Mars's subsurface ice reserves are enough to terraform the entire planet. Some calculations suggest there might not be enough water ice to create Earth-like oceans on Mars. The polar ice caps contain water, but maybe not enough. This means you might need to import water. You could redirect icy asteroids toward Mars. You could crash them into the surface, adding water and energy. You'd need to do this on a scale that's almost incomprehensible, dozens or hundreds of large asteroids over centuries. But it's possible. Asteroid redirection technology is feasible in principle. We've already successfully landed spacecraft on asteroids. We could eventually develop technology to push asteroids. Here's another issue: Mars's low gravity. Mars's gravity is only 38% of Earth's. This means the atmosphere would be harder to hold on to. Gas molecules escape more easily. Over time, even a thick Martian atmosphere would gradually leak away into space, especially without a magnetic field to protect it. This is solvable but challenging. You could regenerate the atmosphere constantly. You could accept that you'd need to maintain the terraform indefinitely, continuously adding greenhouse gases and atmospheric constituents. Or you could develop technologies to create or maintain a magnetic field. Some scientists have proposed placing large magnets in orbit to create an artificial magnetic field. This would protect Mars's atmosphere from solar wind erosion. There's also the issue of the Martian soil. The regolith is oxidized. It's not great for plants immediately, but you could improve it. You'd add organic matter, you'd add bacteria and microorganisms. Over time, you'd build actual soil from the Martian regolith. Here's something interesting. There are organisms on Earth that could survive on Mars, even in its current state. Extremophile bacteria, lichens. These hardy organisms could be seeded on Mars now and survive. They wouldn't thrive, but they could exist. As you terraformed, you deliberately add life. Introduce plants, simple organisms first, then more complex ones. Eventually, Earth-like biosphere would develop. But this would take thousands of years. The fascinating part is that this process would be partially self-sustaining. Once you have plants producing oxygen, once you have a biosphere, the system would maintain itself to some degree. You wouldn't need to keep adding greenhouse gases forever. Life would take over the process. But there's a question here. Should we? Should we terraform other planets? This is where things get philosophical and ethical. On one hand, terraforming other planets would be an extraordinary achievement. It would provide homes for humanity. As Earth's population grows, as resources become strained, having another habitable world would be transformative. It would reduce pressure on Earth. It would expand human civilization beyond Earth. It would also be incredibly interesting scientifically. We'd learn about planetary atmospheres, climate science, geology, astrobiology. The technology we'd develop would have applications on Earth. We'd solve climate problems on one planet that would help us manage our climate on another. On the other hand, there are objections. First, there's the question of planetary preservation. Some scientists argue that Mars should be preserved in its natural state. It has scientific value as an untouched world. If we terraform it, we destroy what it is. We turn it into a copy of Earth. This is related to the concept of planetary protection. Currently, when we send spacecraft to other planets, we sterilize them to avoid contaminating those worlds with Earth microbes. We try to keep other worlds pristine. Some people argue we should extend this philosophy to protection of entire planets. Second, there's the question of life. If Mars ever had microbial life, or if it has life now that we haven't detected, should we destroy that by terraforming? Should we preserve Martian life, however primitive, rather than replacing it with Earth life? This connects to astrobiology. If we discovered that Mars had life, finding a second origin of life would be revolutionary. It would tell us that life arises readily in the universe. It would have profound implications for how common life is. Should we sacrifice that scientific discovery to terraform the planet? Third, there's the practical question. Terraforming is monumentally expensive. It requires centuries or millennia of effort. It requires resources. It requires technology we don't have. Should humanity invest those resources in terraforming when we have problems on Earth? Climate change, poverty, disease. Shouldn't we fix Earth first? These are legitimate questions. There's no clear answer. Different people have different values and priorities. My perspective is that these aren't necessarily binary choices. We don't have to choose between fixing Earth and developing terraforming. We could do both. The technology we develop for terraforming could help us address Earth's climate. The resources could come from a more advanced civilization that has already addressed Earth's problems. Also, terraforming wouldn't happen in the immediate future. It would be a project for centuries or millennia from now. By then, maybe humanity will have solved Earth's current problems. Maybe we'll have the resources and capability to pursue both Earth restoration and planetary terraforming. But let's talk about the actual obstacles, the real engineering challenges. One huge challenge is that we don't have the infrastructure to terraform Mars yet. We don't have factories on Mars producing greenhouse gases. We don't have mining operations extracting resources. We don't have ways to land huge quantities of equipment. We'd need to build this infrastructure first. We'd need initial settlements on Mars, people who maintain equipment, scientists who monitor progress, engineers who adjust systems. This initial phase might take decades or centuries. Getting humans to Mars, establishing permanent bases, developing the technology. Only after this foundation is laid could actual terraforming begin. Another challenge is monitoring and control. You'd need constant observation and adjustment. If the planet is warming too fast, you'd need to reduce greenhouse gas production. If it's warming too slowly, you'd need to increase it. You'd need sensitive instruments measuring atmospheric composition, temperature, pressure, water content. You'd need to ensure the process was proceeding as planned. This would require continuous communication with Mars, which is feasible with our current technology, but would require significant infrastructure. There's also the challenge of timescales. We're talking about projects that would take thousands of years. How do you maintain a project for thousands of years? How do you ensure that future generations continue the work? How do you maintain institutional knowledge across centuries? This is partly a civilization question. It's about whether human civilization can commit to long-term projects. Some historical examples are not encouraging. Many institutions that lasted for centuries have collapsed, but some have persisted. Some knowledge has been transmitted across millennia. It's unclear whether we could maintain a terraforming project for thousands of years. But it's not impossible. There's also the challenge of unexpected consequences. When you make planetary scale changes, you can get unintended results. On Earth, we've seen climate change have unexpected effects. Ecosystems respond in surprising ways. Species behave differently than predicted. The same could happen on Mars. You start a process thinking you know what will happen, but the planet surprises you. You might need to adjust strategies. You might need to solve problems you didn't anticipate. This argues for going slowly, for monitoring carefully, for being willing to pause or adjust the process if unexpected issues arise. But here's something important. Many of the obstacles aren't physics problems. They're not fundamental limitations. They're engineering and logistics problems. And humans have proven remarkably good at solving those. Building the infrastructure for terraforming would be challenging, but not impossible. We could do it if we committed the resources. The timescales are long, but they're manageable within the span of human civilization. Let me tell you about some specific terraforming proposals that scientists have actually developed. There's the Zubrin proposal, developed by engineer Robert Zubrin. This is a specific engineering plan for terraforming Mars. Zubrin's approach is to use factories that produce powerful greenhouse gases like CFCs. These factories would be powered by solar panels or nuclear reactors. They'd run for decades or centuries, gradually releasing CFCs into the atmosphere. CFCs are incredibly powerful greenhouse gases. A small amount goes a long way. You wouldn't need to produce enormous quantities. But over time, the accumulation would be significant. Zubrin calculated that in about 100 years, factories of this type could raise Mars's temperature enough to start melting the polar ice caps. Not completely, but enough to get a runaway greenhouse effect going. Once the ice caps start melting, they release carbon dioxide. This adds to the greenhouse effect. Temperatures rise more ice melts. Positive feedback takes over. The process accelerates. Zubrin's timeline is faster than some other proposals. He suggests you could have a Mars with breathable atmosphere and comfortable surface temperatures in a few thousand years. Not tens of thousands, a few thousand. This is still an enormous timescale, but it's shorter than some scientists propose. It suggests terraforming might be more feasible than sometimes assumed. Another proposal focuses on asteroids. The idea is to direct icy asteroids and comets toward Mars, crash them into the surface. Each impact adds water, adds heat, adds energy. Over centuries, hundreds of targeted asteroid impacts would gradually transform Mars. The water would accumulate, creating lakes and eventually oceans. The impacts would add heat. The dust and debris would affect the climate. This is more dramatic and unpredictable than greenhouse gas production, but it's efficient. Redirecting asteroids could add enormous amounts of water and energy with relatively little effort once you have the technology. There's also biological terraforming. Some scientists propose that you could begin terraforming Mars by introducing microbial life. Cyanobacteria, for example. These bacteria photosynthesize. They take carbon dioxide and produce oxygen. If you seeded Mars with cyanobacteria, they could slowly transform the atmosphere. Over thousands of years, they'd gradually increase oxygen levels and decrease carbon dioxide. This would change the chemistry of the planet. The advantage of this approach is it's partially self-sustaining. Life does the work, not factories. The disadvantage is it's slow, slower than artificial methods, but you could combine approaches. Artificial warming to create conditions where life can flourish. then biological processes to take over the terraforming, humans providing the initial conditions, then life running with it. Here's something fascinating. We don't even need Mars's existing resources if we're willing to invest enough energy. You could theoretically terraform Mars with minimal use of Martian materials. You could import everything: water, gases, soil organisms. You could build it from scratch. This would be monumentally expensive, but it's theoretically possible. You'd be building an entire biosphere from imported components. It would take longer than using local resources, but it could be done. This is important because it means terraforming isn't limited by what Mars has. It's limited by human will and resources. Let me talk about what a terraformed Mars might look like thousands of years from now. Imagine standing on the surface of Mars in the year 4000. The sky is blue, not the butterscotch color of current Mars. There are clouds, not clouds of dust, but water vapor clouds. The temperature is mild, maybe 20 degrees Celsius. Comfortable. You don't need a spacesuit. You breathe through an oxygen mask, but the external pressure isn't lethal. There are lakes. In the low areas, there are actually oceans. The northern polar region has been flooded. The Great Basin of Hellas Planitia has become a sea. The soil supports vegetation. There are lichens, mosses, grasses, perhaps even trees in sheltered areas. The biosphere is still primitive. It's not Earth with all its complexity, but it's life, it's breathing. There are human cities, domes at first, but eventually open air structures as the atmosphere thickens. Humans walk outside in light clothing, oxygen masks, but no heavy suits. They breathe Martian air, supplemented with oxygen. The red dust is still there, but it's mixed with organic matter now. Soil that supports life. The ancient riverbeds flow with water again. The Valles Marineris is a vast canyon with streams and maybe a river system. Over thousands of years from that point, the process would continue. The atmosphere would thicken more. Oxygen levels would increase. Eventually, maybe after 10,000 years or more of terraforming, you could breathe without oxygen masks. The pressure would be high enough. The oxygen percentage would be high enough. Eventually, Mars would be genuinely habitable. You could walk outside in light clothes. You could drink water. You could grow crops without domes. You could raise children who had never seen Earth, who knew Mars as their home. This is the vision. This is what terraforming aims for. But I want to be clear, this is far in the future. Thousands of years. Not something that's happening now. Not something that will happen in the next century. Even the initial stages of Mars colonization are decades away. We haven't yet landed humans on Mars, let alone established permanent settlements. Terraforming proper probably wouldn't begin until the 23rd or 24th century at the earliest. But it's possible. The physics works. The engineering is challenging but not impossible. The timescales are long but manageable. There's also a question of whether we should terraform in the way I've described, or whether we should do something more gradual. Some scientists propose para-terraforming. Para-terraforming is an intermediate approach. Instead of terraforming the entire planet, you create large-scale habitats. You build massive domes or enclosed structures covering large areas. Within these structures, you create Earth-like conditions. You might build a dome covering an area the size of a state. Inside, you create atmosphere, water, soil, life. Outside remains Martian, but inside, humans live in Earth-like conditions without needing spacesuits. This approach is more feasible in the near term. You could build para-terraformed habitats in the 22nd century, perhaps. Full terraforming might require another 1,000 years. Para-terraforming has advantages. It's faster, it's cheaper, it requires less commitment over longer timescales. It provides habitable space for humans without needing to transform an entire planet. But it's also less ambitious. It's accepting that Mars will remain mostly Martian, just with Earth like areas within artificial structures. Both approaches might happen. You might have para terraformed cities while full terraforming proceeds slowly in the background. Okay, let me talk about whether any planets in other star systems could be terraformed, because the Milky Way has billions of planets. Could we terraform any of those? The short answer is not with our current technology or any technology we can conceive of in the near future. Terraforming is already an extraordinary undertaking for Mars, which is only light minutes away. For planets around other stars, which are light years away, it becomes incomprehensibly difficult. The timescale to send human missions to other star systems is centuries or millennia at minimum. We don't have propulsion technology to do it yet. Even if we did, reaching another star system would take generations. Then terraforming would take thousands of additional years. You're looking at timescales of tens of thousands of years or more just to establish settlements and begin the process. This is beyond what we can reasonably plan for. Even thinking about terraforming other planets in our own system is ambitious. Thinking about other star systems is pure speculation. But it's not impossible in principle. Sufficiently advanced civilizations, thousands or millions of years from now, might terraform planets around other stars. It would just require technologies and resources we can barely imagine. Let me talk about the ethical implications of terraforming, because this is important. There's an environmental ethic that values nature for its own sake. The argument goes, nature has value beyond its utility to humans. We should preserve natural systems, even if Mars is lifeless. It has scientific value. It has aesthetic value. We shouldn't transform it just because we can. This is a legitimate perspective. Some people believe we should preserve the solar system in its natural state. We should explore, study, understand, but not fundamentally alter. Others take a different view. They argue that expanding life and consciousness to other worlds is inherently valuable. Creating habitable worlds, creating new homes for humanity and Earth life is worthwhile. It expands the biosphere. It reduces risk by spreading humanity across multiple worlds. There's also a utilitarian argument. Terraforming solves problems. It provides resources. It provides living space. It reduces pressure on Earth. For a growing human civilization, these are significant benefits. There's also the argument that natural is a human concept. Mars is not some pristine Eden. It's a dead rock, has been for billions of years. Terraforming it isn't destroying something alive. It's creating life where there is none. These different perspectives value different things. There's no objectively correct answer. Different people will reach different conclusions based on their values. But I think it's worth noting that we do alter nature on Earth constantly. We create cities, farms, irrigation systems. We've transformed vast areas of Earth. We're not particularly good at preserving nature even when we try. Given that, it seems inconsistent to say we should absolutely preserve Mars while accepting massive transformation of Earth. Either we value nature preservation, in which case we should do both, or we accept that transformation is acceptable, in which case terraforming is morally permissible. My personal view is that some exploration and terraforming of the solar system is acceptable, as long as we preserve some worlds for scientific study and preserve Earth's environment. We should get the best of both worlds, maintain Earth's biosphere, study some worlds in their natural state, and develop others. But that's just one person's opinion. Let me tell you about something interesting. There are Mars cave systems that could be habitable immediately, or nearly so. Some of the deep caves on Mars might have temperatures approaching the global average. They might provide shelter from radiation. They might contain underground water ice. It's possible that deep caves could provide habitats that are nearly Earth-like or could be made Earth-like with modest effort. This is called natural terraforming, using existing Martian features to create habitable spaces rather than transforming the entire planet. Some scientists think the first permanent human settlements on Mars might be in caves. Underground, protected from radiation, with water ice access, these caves could support human habitats. This is more feasible than surface terraforming. You could have humans living in Martian caves in the next century or two, arguably. Full terraforming would take thousands of years. So there's a spectrum from most feasible to least feasible. 1. Underground habitats in Mars caves, next century or two. 2. Para-terraformed domes and enclosed cities, 22nd to 23rd century. 3. Partial surface terraforming, 23rd to 25th century. 4. Complete Mars terraforming, several thousand years. 5. Venus terraforming, 10,000 plus years. 6. Terraforming moons, thousands to tens of thousands of years. 7. Terraforming planets in other star systems, tens of thousands of years minimum. Each step is progressively more ambitious and further in the future, but each is, in principle, possible. Here's something important. Technology advances. Methods that seem impossible now might become feasible. In the 1800s, space travel seemed impossible. In the 1900s, before World War II, building spacecraft seemed impossible. Now we do it routinely. Our descendants will have technologies we can't imagine, methods for terraforming that we haven't conceived of, different approaches, different timescales. What seems impossibly difficult to us might seem routine to them. So even our estimates of how hard terraforming is might be optimistic or pessimistic compared to what will actually be possible. The point is, terraforming is a long-term project. It requires commitment across centuries or millennia. It requires technology that's advanced but not magical. It requires accepting and managing planetary scale consequences. But it's not impossible. It's a genuine possibility for humanity's future. Let me talk about one more thing: the relationship between terraforming and climate engineering on Earth. Climate engineering, or geoengineering, is making deliberate changes to Earth's climate to address global warming. Methods include injecting particles into the upper atmosphere to reflect sunlight, fertilizing oceans to increase carbon dioxide absorption, building giant reflectors in space. Some of these are the same technologies we'd use to terraform other planets. Orbital mirrors, for example, greenhouse gas manipulation, biological processes, so developing one could inform developing the other. Learning to terraform Mars could teach us about controlling Earth's climate. Learning to fix Earth's climate could teach us about terraforming Mars. This is another argument for pursuing terraforming research. Even if we never terraform Mars, the technology we develop would have applications on Earth. It could help us manage climate change. It could help us restore damaged ecosystems. Conversely, our experience managing Earth's climate might teach us not to terraform. Climate change has shown us how difficult it is to predict and control planetary systems. Unintended consequences are common. If we can't control Earth's climate despite knowing it well, how can we control Mars? This is a fair point, but I'd argue that Mars would be easier in some ways. It's simpler, fewer variables, no existing biosphere to protect, no billions of people depending on the outcome. We could make mistakes on Mars without catastrophic consequences. Earth is the test case for planetary management. Mars is the second case where we'd apply what we learned. There's also the question of why terraform at all? Why not just build enclosed habitats? Why not create artificial environments without transforming the planet? The answer is you could. Paraterraforming could provide all the habitable space humans need. It might be easier than full terraforming. But there's something appealing about an actual habitable world, a world where humans can walk outside without protection, where life thrives in natural cycles. It's not just practical, it's aspirational. It speaks to something deep in human nature, the desire to expand, to create, to build a new world. Plus, a fully terraformed world would be self-sustaining. A biosphere would maintain itself. Enclosed habitats require continuous maintenance and power input. They're dependent on technology. A terraformed world would depend on nature. So there are both practical and philosophical reasons to pursue full terraforming rather than just artificial habitats. Let me wrap up by talking about Mars's future. What will actually happen? I think the most likely scenario is this. Over the next century or two, humans will establish permanent settlements on Mars, initially in enclosed habitats, eventually in underground caves if those prove more feasible. Over the following centuries, human presence will expand. More settlements, more infrastructure, mining operations, manufacturing, scientific research. At some point, probably in the 22nd or 23rd century, deliberate terraforming will begin. It might start with simple measures, releasing a small amount of greenhouse gas from a factory, placing reflectors in orbit, introducing hardy microbes. Over centuries, the process will continue. The planet will gradually warm, the atmosphere will thicken, life will expand. Para-terraformed domes will house growing populations. Gradually, as the planet becomes more hospitable, surface habitats will become more feasible. Eventually, humans might walk outside without spacesuits, at least briefly, with oxygen support. By the year 5,000 or 10,000, Mars might have a climate and biosphere genuinely similar to Earth's. It might have oceans, complex ecosystems, cities under open sky. But this is speculative. We don't know what will actually happen. Technology might advance faster or slower than expected. Resources might be more or less available. Human society might prioritize space exploration or might not. We might discover life on Mars and choose to preserve it rather than terraform. We might develop technologies that make terraforming unnecessary. We might decide it's not worth it, but it's possible. That's the key point. If humanity commits to it, if we develop the technology and dedicate the resources, we could terraform Mars. We could create a second habitable world. We could expand life and consciousness beyond Earth. That's a profound possibility. That's what makes terraforming worth thinking about. Let me go deeper into the specific engineering required. Because while the big picture concept is clear, the details are fascinating and revealing. Starting a Mars greenhouse requires understanding what happens when you introduce gases into a thin atmosphere. When you release CFCs or methane, they disperse. Some escape to space. Some settle and remain. Some react with other compounds. The chemistry is complex. Scientists have calculated that to warm Mars significantly, you'd need to release about 1 million tons of CFC-12 annually. That sounds like a lot, but consider this. Earth's CFC emissions before the Montreal Protocol were much higher. We were producing hundreds of thousands of tons annually. So the engineering to produce these gases on Mars is theoretically possible using technology we already have. However, you'd need factories on Mars. You'd need raw materials. You'd need power. You'd need maintenance over centuries. This is the logistical challenge, not the physics, but the sustained human effort. Building the infrastructure on Mars to support terraforming is a massive undertaking. First, you need spacecraft to land equipment. Current rockets can carry maybe 20 to 30 tons to Mars. To build significant terraforming infrastructure, you'd need to land hundreds or thousands of tons of equipment. You'd need reusable rockets, efficient launches, and decades of preparation. Once on Mars, you'd need to construct factories. You'd need power sources. Solar panels would work, but might get dusty. Nuclear reactors would work better. You'd need cooling systems, maintenance crews, spare parts. The engineering is challenging but achievable. You'd also need to monitor progress. You'd need instruments measuring atmospheric composition, temperature, pressure, radiation levels. You'd need to transmit data back to Earth. You'd need Earth-based teams analyzing data and making decisions about adjusting the terraforming process. This creates a feedback loop. Instruments measure conditions. Data goes to Earth. Teams analyze and make recommendations. Commands go to Mars. Equipment adjusts. New measurements are taken. Over centuries, this loop continues. One thing people don't always appreciate is that the process would have to be responsive. You can't just set a terraforming program and leave it alone. Unexpected things happen. Equipment breaks. Processes accelerate or slow. The planet surprises you. You need humans or AI systems continuously monitoring and adjusting. Let me talk about the role of AI in terraforming, because honestly, by the time we're terraforming planets, we'll probably have artificial intelligence that's far beyond what we have now. AI systems could monitor Mars continuously. They could make adjustments, they could run factories, they could maintain equipment. In fact, terraforming might be one of the first large-scale projects handled primarily by AI. Humans would provide oversight and make major decisions, but day-to-day management would be handled by AI systems. This makes sense because the project is so long-term and complex. Imagine artificial intelligences that have been monitoring Mars for centuries. They understand the planet's systems intimately. They know exactly what adjustments to make to progress toward the terraforming goals. They can operate factories, maintain equipment, optimize processes. Humans would check in periodically, adjust the overall strategy, make major decisions, but the continuous work would be done by machines. This is actually encouraging for terraforming feasibility. If we develop good AI, the long-term project management becomes more tractable. Humans don't have to continuously commit resources. AI can handle the details. Humans can oversee and occasionally adjust course. Let me talk about the role of robots and automation. Because Mars is harsh. It's not a pleasant place to work. Robots are much more practical than humans for most terraforming work. Robots could construct factories. They could mine ice and extract it from the subsurface. They could build power generation systems. They could maintain equipment. They could do most of the physical work of terraforming. The advantage is that robots don't need life support. They don't need to breathe. They don't need food or water or shelter. They're far more efficient than humans for working in harsh environments. Humans would eventually settle on Mars, but initially, and during the terraforming phase, most of the work would be done by robots. Humans might arrive to establish initial bases, then robots would take over. Humans might return periodically for maintenance or to expand operations. This changes the timeline somewhat. You don't need large human populations on Mars initially. You need robots. That's more feasible in the near term. Let me talk about a specific challenge: the problem of the faint young sun. This is relevant to understanding terraforming more broadly. Early in the solar system's history, the sun was fainter. It put out less energy. Yet evidence suggests Mars had liquid water, suggesting it was warm. How could Mars be warm if the sun was fainter? The answer is the greenhouse effect. Mars had a thicker atmosphere with more greenhouse gases. This kept it warm despite the fainter sun. As the sun brightened, Mars should have gotten warmer, but instead Mars cooled. Why? Because the atmosphere was lost. Mars lost its magnetic field. The solar wind stripped away the atmosphere. The planet cooled. Liquid water disappeared. Mars became the frozen desert we see today. This is a cautionary tale. An atmosphere doesn't persist forever. Planets can lose them. Mars experienced this naturally. If we terraform Mars, we need to accept that we might need to maintain the atmosphere indefinitely. Solar wind will continue to strip it. We might need to periodically replenish it. This is a long-term commitment, not just thousands of years of creating the atmosphere, but potentially indefinite maintenance after that. We'd need to keep the terraforming going forever, or at least for as long as we want Mars to be habitable, unless we solve the magnetic field problem. If we can create an artificial magnetic field on Mars, we can protect the atmosphere from solar wind erosion. Some scientists have proposed placing large superconducting magnets in Mars's orbit to create a planetary magnetic field. This would require incredibly powerful magnets and enormous amounts of power. But it's theoretically possible. With an artificial magnetic field, Mars could hold on to its atmosphere. The terraforming would become more stable. Let me talk about what the first humans on Mars would be like compared to what terraformed Mars would be like, because this distinction is important. The first humans on Mars would be like astronauts on the moon. They'd be in suits. They'd be in habitats. They'd be explorers. They'd be scientists studying the planet. They wouldn't be living in a habitat they built themselves. They'd be depending on resupply from Earth. As Mars developed, permanent settlements would be established. Habitats would be constructed. Mining would begin. Manufacturing would start. Mars would develop an economy. Trade with Earth. Self-sufficient farms and industries. But people would still be in habitats, still wearing suits to go outside, still depending on technology to survive. In a terraformed Mars, humans would live in the open. They'd build cities on the surface. They'd farm in the open air. They'd not need suits. Their children would know Mars as a habitable world, not an alien wasteland. This is a fundamental difference. It's the difference between visiting a place and living there naturally. It's the difference between a colony and a world. Let me talk about the psychological impact of terraforming, because this is profound. Knowing that you're transforming an entire world, that you're creating oceans and ecosystems and breathable air, that you're expanding life across the solar system, that's powerful. It changes how people think about themselves and their civilization. On Earth, environmental destruction is sometimes justified by short-term economic gains. extracting resources, polluting, destroying habitats. We've become pessimistic about nature. We assume destruction is inevitable. But terraforming is creating, it's building, it's expanding life and habitability. It's the opposite of destruction. It might actually shift human psychology. It might make us more capable of environmental restoration. If we can terraform Mars and create ecosystems, maybe we can restore damaged ecosystems on Earth. There's also the pride and meaning. Being part of a civilization that transforms planets, that's extraordinary. It gives meaning to existence. It's a project worth dedicating to. It unites humanity around a common goal that transcends national boundaries and current conflicts. This is perhaps underappreciated. The terraforming project isn't just an engineering feat, it's a civilization level endeavor. It's something humans can be proud of. It's something that could bind humanity together. Let me discuss the relationship between terraforming and settlement patterns. How would terraformed Mars actually be colonized and developed? The first phase is exploration and small settlements. Bases near good locations, near water ice, near resources, near good landing sites. The second phase is expansion, more settlements, infrastructure development, mining operations, factories, power generation. The third phase is terraforming initiation. Factories begin producing greenhouse gases. Biological seeding begins. Asteroid impacts begin, if you're using that method. The fourth phase is active terraforming. The planet is warming. The atmosphere is thickening. Life is expanding. This lasts thousands of years. During this time, human settlements expand greatly. Population grows, culture develops. Mars becomes an inhabited world. The fifth phase is completion. The planet is habitable. Humans can live in the open. The biosphere is complex. Settlement patterns shift. Cities grow in good locations. Civilization develops. Each phase has its own challenges and opportunities. In the early phases, the emphasis is on resource extraction and survival, getting enough resources to survive, establishing permanent habitats. In the middle phases, the emphasis is on infrastructure, building the systems that will terraform the planet, establishing industries, growing population. In the later phases, the emphasis is on civilization building, culture, art, science, governance. Mars becomes a world with its own identity, separate from Earth. This is fascinating from a historical perspective. We'd be watching the birth of a new civilization. We'd have records of the entire process. We'd see how humans adapt to a new world, how culture develops, how society organizes. It would be one of the most significant events in human history. More significant than the colonization of the Americas, because this is colonizing an entire planet and transforming it. It's the beginning of human expansion beyond Earth. Let me talk about the economic case for terraforming. Is it worth the investment? Economically, terraforming is an enormous undertaking. It would require vast resources, billions or trillions of dollars, centuries of effort. But consider the benefits. A new habitable world, resources extracted from Mars, space for population expansion, a backup for human civilization, insurance against catastrophe on Earth. The economic return would be long term. You wouldn't see profits in decades or centuries. You'd see them in thousands of years. But eventually, a terraformed Mars would be incredibly valuable. Its real estate, its resources, its living space. Compare it to Earth colonization. European nations spent enormous resources colonizing the Americas. It took decades or centuries to see economic returns, but eventually it was immensely profitable. The colonies grew, They became wealthy. They became powerful nations. Terraforming Mars would be similar, but on a longer time scale. The investment would be enormous, but the eventual returns would justify it. A second habitable world is valuable beyond measure. From a civilization perspective, it's an investment in the future. It's saying we believe in human civilization lasting thousands or millions of years. We believe we're worth expanding beyond Earth. We're worth the effort. This is not a decision the current generation would make, but future generations might. When technology is more advanced, when resources are more abundant, when human civilization is more stable, then the terraforming project might begin in earnest. Let me talk about potential problems and how they might be solved. Problem: Mars doesn't have enough water to create Earth-like oceans. Solution: import water via asteroid redirection. Problem: Mars's gravity is too low to hold an atmosphere indefinitely. Solution: create an artificial magnetic field to protect the atmosphere, or accept that you need to maintain the atmosphere indefinitely. Problem: the radiation is dangerous to life. Solution: thick atmosphere blocks radiation. Ozone layer develops over thousands of years, similar to Earth. Problem: soil isn't good for plants initially. Solution: add organic matter. Add bacteria and microorganisms. Build soil over time. This is natural soil formation, just accelerated. Problem: Mars is far from Earth, making communication and resupply difficult. Solution: over time, Mars becomes self-sufficient, less dependent on resupply from Earth. Eventually, Mars is economically independent. Problem: the project takes thousands of years. How do you maintain commitment? Solution: develop good governance and institutions that last. Use AI to handle long-term management. Build culture that values the terraforming goal. Problem: unexpected consequences might require major changes to approach. Solution: monitor continuously. Be prepared to adjust strategy. None of these problems are unsolvable. They're challenges, yes, but they're addressable with sufficient technology and commitment. Let me talk about what would actually grow on terraformed Mars. What would the ecosystem look like? Initially, you'd plant hardy microbes, bacteria, and archaea that can survive harsh conditions. These would begin breaking down rock, creating soil. They'd start processing gases. They'd start building the foundation for more complex life. After centuries, you'd introduce lichens and mosses. These are incredibly hardy. They can live on bare rock. They can tolerate extreme conditions. As they break down rock and build soil, they'd prepare the way for plants. After more centuries, you'd introduce grasses, shrubs, and hardy vegetation. Plants that can tolerate cold and thin air initially, but that thrive as conditions improve. Eventually, you'd have forests, not immediately, but over thousands of years. As the climate warmed and the atmosphere thickened, more complex plants would thrive. Animals would come later. Once there's enough vegetation, you could introduce insects, then larger animals. The ecosystem would build gradually, but the first life would be microbial. Bacteria would do the heavy lifting. Microbes would transform the planet in fundamental ways. Then higher life would build on that foundation. This is actually how Earth's biosphere developed. Microbes dominated for billions of years. They transformed Earth's atmosphere from carbon dioxide and methane to oxygen. They created the conditions for higher life. Then higher life developed. Terraforming Mars would follow a similar pattern: microbes first, then progressively more complex life. The result, after thousands of years, would be a biosphere somewhat similar to Earth's, maybe 30% as complex, maybe with different species composition because you'd be introducing Earth species carefully, but recognizable as a living world. Let me talk about one more fascinating aspect: how terraforming might affect Earth. The research required for terraforming would advance climate science tremendously. Methods developed for terraforming, greenhouse gas control, atmospheric engineering, biological systems, would inform Earth climate management. We might develop technologies on Mars that could be used to solve problems on Earth. Carbon capture, atmospheric restoration, bioremediation. The psychological and cultural impact of terraforming might also affect Earth. If we can terraform Mars, we can restore ecosystems on Earth. We can fix damage we've caused. The idea that we can positively transform worlds might inspire us to fix Earth's problems rather than accept environmental degradation. Conversely, if we attempt terraforming and fail or encounter unexpected problems, that might teach us humility. It might show us that planetary systems are more complex than we thought. It might discourage us from making changes to Earth out of fear of unintended consequences. Either way, terraforming would profoundly affect how we understand and relate to our own planet. Let me talk about potential parallels to other big human projects, because terraforming isn't unique in its ambition, just in its scale. The Panama Canal, a massive engineering project that connected two oceans. It reshaped global trade. It took enormous resources and decades of effort. But it was achievable with 20th century technology. The Great Wall of China, built over centuries, millions of workers, enormous resources. But it demonstrated that humanity could commit to long-term projects. The Apollo program landed humans on the moon in a decade, required mobilizing vast resources and talent, showed what's possible with national commitment. Terraforming is like these projects, but on a much larger scale and much longer time scale. It requires the commitment shown in Apollo, the long-term persistence shown in the Great Wall, the transformative impact shown by the Panama Canal. But it's achievable. Humans have demonstrated the ability to do transformative engineering projects. Terraforming is in that tradition. It's ambitious, yes, but it's within human capability if we commit to it. Let me also talk about what terraforming tells us about human nature, about where we're headed as a civilization. The fact that we even conceive of terraforming suggests something about human nature. We're not content with what we find. We want to change things. We want to expand. We want to create. This can be negative. It's the same impulse that leads to environmental destruction. But it can also be positive. It's the impulse that leads to building cities, creating art, advancing science. Terraforming represents the ambition of the human species. It says we believe our civilization is worth expanding, that we're worth spreading across the solar system, that we're capable of great things. Whether that's actually true is debatable. But the ambition itself is telling. It reflects how we see ourselves. If we actually terraformed Mars, it would be one of the greatest achievements in human history. Not just technologically, but philosophically. We would have proven that humans can take on projects of cosmic scale. We would have shown that consciousness can reshape worlds. That's profound. That's something to contemplate. Let me end by talking about timescales one more time, because this is crucial to understanding terraforming. Humans think in timescales of years or decades. Our governments plan in timescales of decades. companies in timescales of years. Even universities plan in centuries at most. Terraforming requires thinking in timescales of thousands of years. This is very difficult for humans. It's outside our normal frame of reference. We don't have historical precedent for projects that take thousands of years, yet it's not impossible. It requires different institutional structures. It requires accepting that we won't see the results in our lifetime. It requires commitment to a goal that benefits future generations will never meet. This is actually a valuable exercise for humanity. It forces us to think long term. It forces us to consider the future. It makes us think about what kind of civilization we want to be. Do we want to be one that only considers the next decade, or one that thinks thousands of years ahead? Terraforming, in a sense, is a test of whether humanity can think long term. Can we commit to multi-generational projects? Can we work toward goals that benefit people centuries from now? If we can, terraforming becomes possible. Not just possible physically, but possible as a social project. We could actually do it. If we can't, then terraforming will remain a beautiful dream, something we think about but never attempt. A road not taken. I think humanity is capable of thinking long term. I think we can commit to multi-generational projects. We've done it before, historically. We can do it again. So I believe terraforming is possible, not just physically, but as a human endeavor. Let me go deeper into specific terraforming scenarios for different worlds, because each presents unique challenges and opportunities. Mars, as I've discussed, is the primary terraforming candidate, but the details matter. Let's say you're the project director for Mars terraforming in the year 2500. What's your actual plan? Phase 1, years 2500 to 2600. Establish infrastructure, land factories, build power generation, establish monitoring systems, deploy initial robot teams. This phase is about creating the capacity to terraform. Phase 2, years 2600 to 2800. Begin greenhouse gas production. Factories start producing CFCs and methane. Orbital mirrors are deployed or expanded. Initial asteroid impacts begin if you're using that method. The greenhouse effect starts to strengthen. Temperatures begin to rise slightly. Phase 3, years 2800 to 3500. Accelerate warming. More factories are built. Production increases. The process begins to self-accelerate. Ice caps start melting. Water vapor enters the atmosphere, increasing greenhouse warming. This is the critical phase where you hope for positive feedback. Phase 4, years 3500 to 4500. Active terraforming. The planet is noticeably warming, significant ice melting, considerable atmospheric thickening. Biological seeding intensifies. Organisms are spreading across the surface, some survival and reproduction. The biosphere is beginning. Phase 5, years 4500 to 8000. Development of biosphere. Life is thriving. The atmosphere is breathable with oxygen masks. Pressure is approaching Earth normal. Oceans form. Ecosystems develop. Human settlements expand greatly. Phase 6, years 8000 plus. Near habitable conditions. Walking outside without a suit becomes possible, with oxygen support initially, eventually full habitability. This phase might take thousands of additional years to reach full completion. This is a 6,000-year project, roughly. At each phase, things can go wrong. Equipment breaks. Unexpected consequences arise. You need to adapt. but the basic trajectory is toward habitability. Now let's talk about Venus. Venus is harder, so the timeline is longer. Venus terraforming might begin around year 3000 or later, much later than Mars because Mars is easier. Venus requires cooling first. You'd place enormous sunshades in orbit. You begin removing greenhouse gases from the atmosphere. This would take thousands of years. The planet would gradually cool. Once cool enough that liquid water could exist, you'd begin water accumulation. You'd harvest water from water vapor in the upper atmosphere or import it via asteroid. Gradually, oceans would form. You'd need to deal with sulfuric acid clouds. Chemical processes could convert sulfuric acid into other compounds. Or you could wait for the sulfuric acid to gradually fall to the surface as the atmosphere cooled and changed. Venus terraforming would probably take 10,000 to 50,000 years, much longer than Mars. The engineering is much harder, but again, it's not impossible. It's just harder. Now let's talk about the moons. Europa and Enceladus have subsurface oceans. Titan has surface methane oceans. For Europa, the ocean is under kilometers of ice. To create a habitable ocean accessible from the surface, you'd need to 1. Warm the moon using orbital mirrors or other methods. 2. Melt the ice from the inside, creating a liquid ocean. 3. Keep it warm enough to remain liquid. 4. Eventually, make the surface habitable. This would take thousands of years. Europa would become a water world. Humans could eventually live in the ocean or create habitats on the thin ice crust. For Enceladus, similar approach. It's a smaller moon, so warming it might be easier or harder, depending on how you do it, but fundamentally similar challenges. For Titan, the situation is different. Titan already has an atmosphere. It already has liquid methane and ethane oceans. If you warmed it just a few dozen degrees, you could make it habitable for life adapted to methane rather than water. Some scientists believe that if Titan warmed, life based on methane biochemistry could theoretically exist there. This is more speculative, but it suggests multiple pathways to habitability. Let me talk about the role of genetic engineering in terraforming, because as we get more capable at engineering life, this becomes relevant. Currently, terraforming would use Earth organisms. Bacteria, plants, animals selected for their ability to survive harsh conditions. We'd seed these on Mars or other worlds and hope they adapt. But in the future, we might engineer organisms specifically for terraforming. Bacteria that thrive in Martian conditions. Plants that grow rapidly in thin atmosphere. Trees that tolerate cold and low light. This could accelerate terraforming. Instead of waiting for evolution to adapt Earth organisms, we'd create organisms already adapted. This raises ethical questions. Is it okay to deliberately engineer life? Is it ethical to populate worlds with engineered organisms? I think the answer is probably yes in the context of terraforming. We're not harming existing ecosystems because most of these worlds don't have complex life. We're creating new life. We're expanding the biosphere, but it's worth thinking about carefully. The decisions we make now about whether to engineer terraforming organisms could have enormous consequences later. Let me talk about human culture on terraformed worlds, because after thousands of years, the people living there would develop their own culture separate from Earth. Imagine Mars in the year 8000, hundreds of millions of humans living there, multiple independent cities, multiple nations or governments, their own art, music, literature, their own history and traditions. They would be descendants of Earth humans, but they would be Martian. They would have never seen Earth. They would be adapted to Martian gravity, Martian light, Martian environment. Over thousands of years, genetic differences might accumulate. Martian humans might become slightly different from Earth humans. Not dramatically, but different. They would have their own philosophy about Mars. They would see themselves as Martians, not as Earth colonists. This divergence of human culture would be one of the profound consequences of terraforming. We wouldn't just be creating a new world, we'd be creating a new human culture, a new branch of humanity. This is actually valuable. It means if something catastrophic happened to Earth, humanity would survive on Mars. We'd be an interplanetary species, insurance against extinction. Let me talk about whether we might make mistakes in terraforming, because we will. Climate change on Earth has taught us that planetary systems are complex. Unintended consequences happen. Species behave unexpectedly. Ecosystems respond in surprising ways. The same will happen on Mars. You'll introduce organisms, expecting them to behave one way, and they'll behave differently. You'll make adjustments to the atmosphere and get unexpected results. You'll discover that some terraforming method works too well and needs to be adjusted. This is not a reason to avoid terraforming. It's a reason to do it carefully, to monitor continuously, to be willing to adjust strategies. It's also why you want to terraform other worlds first, before turning those same technologies on Earth. You want to learn from Mars. You want to understand what happens when you transform a planet. Then you apply those lessons to managing Earth's environment. Mars becomes a laboratory for planetary engineering. Earth is too important to experiment on directly. Let me talk about the connection between terraforming knowledge and asteroid redirecting. Because if you're going to terraform Mars by crashing asteroids into it, you need to understand asteroids. Asteroid redirection technology is dual use. You can use it to redirect potentially hazardous asteroids away from Earth, or you can use it to redirect asteroids toward Mars for terraforming. The technology is essentially the same. Propulsion systems to nudge asteroids, calculations to determine trajectories, methods to track and monitor. Developing asteroid redirect technology for planetary defense would give you the capability for terraforming. Conversely, terraforming research would improve asteroid defense. This is actually a good reason to develop asteroid redirection technology now. It solves the near-term problem of protecting Earth from impacts. It also builds capability for future terraforming. Many asteroid scientists have pointed out that developing planetary defense should happen anyway for safety. And once you have that technology, terraforming becomes more feasible. Let me talk about the energy budget for terraforming, because energy is fundamental. Terraforming requires energy. To warm Mars, you need to add energy to the system. Greenhouse gases trap energy, but where does that energy come from? The sun. The sun's energy hits Mars. Greenhouse gases trap it. Temperature rises. Venus is harder because you need to remove energy. Sunshades block solar energy. This is possible but requires materials and engineering. The energy requirements aren't astronomical, actually. The solar energy reaching Mars is enormous. If you trap just a small fraction more of it with greenhouse gases, you can warm the planet significantly. The challenge is not energy quantity, but control. Manipulating planetary energy balances with precision. Over thousands of years. This is feasible. Solar energy is abundant. Greenhouse gas concentrations can be controlled. It's an engineering problem, not a fundamental limitation. Let me talk about what we'd learn from terraforming, because the knowledge gained would be valuable. Understanding planetary atmospheres, climate systems, life's adaptability, ecosystem development, soil formation. the requirements for habitability. All of this knowledge would advance science. It would help us understand how planets work, how life adapts, how complex systems develop. On Earth, this knowledge would inform environmental restoration. If we understand how to create an ecosystem on Mars, we understand how to restore one on Earth. It would also inform our understanding of exoplanets. If we terraform Mars, we understand better what happens when a planet is transformed. We can better predict what might happen on distant worlds. We can better understand the conditions that could support life elsewhere. Let me talk about potential timescale scenarios, because there's uncertainty. Optimistic scenario. With advanced technology, strong commitment, and good luck, we could have a breathable atmosphere Mars in 3,000 years. Full habitability in 5,000 years. This assumes good progress in AI, robotics, and engineering. It assumes no major setbacks. Realistic scenario. With moderate technological advancement and reasonable commitment, we're looking at 5,000 to 10,000 years for breathable atmosphere, 10,000 to 20,000 years for full habitability. This assumes some setbacks, but overall progress. Pessimistic scenario. With slow technological progress or reduced commitment, terraforming could take 20,000 to 50,000 years or more. It might never fully complete. It might be abandoned partway through if commitment wanes. All three scenarios are possible. The actual timeline will depend on factors we can't predict. Technology advancement rates, commitment of future civilizations, unexpected problems that need solving, lucky breaks that accelerate progress. But the point is, terraforming is feasible on all timescales. Even the pessimistic scenario gets us a terraformed world eventually. Humanity might need to commit for thousands of years, but it's possible. Let me go into much more detail about Mars's water situation, because water is crucial to terraforming. Mars has water. We know this for certain. Water ice exists in the polar ice caps. Water ice exists in many craters. Water ice likely exists in subsurface reservoirs. But the total amount of water on Mars is uncertain. Some estimates suggest Mars has enough water ice to create oceans covering the entire surface to depths of hundreds of meters. Other estimates suggest there's far less. The uncertainty is significant. If Mars has enough water, you can terraform it relatively easily. The water is already there. You just need to melt it and let it flow. If Mars doesn't have enough water, you have a problem. You'd need to import water. The most practical method would be capturing water-rich asteroids and crashing them into Mars. Over centuries or millennia, you could deliver enormous amounts of water this way. But imagine the engineering. You'd need to identify water-rich asteroids. You'd need to nudge them into Mars' intersecting orbits. You'd need to time the arrivals so they don't all hit at once. You'd need to land them in locations that maximize ocean formation. This is feasible but requires tremendous effort. Multiple asteroid impacts spaced over centuries. The advantage is that each asteroid impact adds energy to Mars, warming the planet. The disadvantage is it's hard to control. Impacts are dramatic events. They change the planet suddenly. You might need to adjust terraforming strategies between impacts. Let me talk about Mars's polar ice caps in detail, because they're central to terraforming. The North Polar ice cap is primarily water ice. It contains frozen water. The South Polar ice cap is primarily carbon dioxide ice, dry ice. There's water ice underneath the carbon dioxide. The North Cap is roughly the size of Greenland. The South Cap is smaller. If you melted all the ice in both polar caps, You'd have enough water to cover Mars to a depth of maybe 10 to 20 meters on average. Some estimates are higher, some lower. The uncertainty is significant. 10 to 20 meters is enough for oceans and lakes, but not Earth-like oceans that cover 70% of the planet. So Mars would need additional water from asteroid impacts to have truly Earth-like oceans. However, 10 to 20 meters of water is still significant. It would create water bodies across the northern plains and in low areas. It would be habitable. It would support ecosystems. It might be enough for human settlements to consider it home. Let me talk about the gases you'd release for greenhouse warming. CFCs, as I mentioned, are powerful greenhouse gases. CFC12 has a global warming potential about 10,000 times that of carbon dioxide. You wouldn't need to produce much to have an effect. Methane is also powerful. Ammonia, various chlorofluorocarbons, perfluorocarbon compounds, all of these trap heat. The advantage of releasing these gases is they're potent. You don't need to produce enormous quantities. The disadvantage is they're toxic to Earth life. Some of them destroy ozone, which is important for Earth. But on Mars, where there's no biosphere yet, the toxicity isn't a concern. Over centuries, as Mars thickened its atmosphere and developed biosphere, you'd eventually reduce and eliminate CFC production. You'd switch to maintaining the atmosphere through biological and industrial processes. But in the initial warming phase, CFCs and similar gases would be your primary terraforming tool. Let me talk about what happens to Mars's dust during terraforming. Mars's surface is covered in fine dust, red dust, rusty dust. It blows around, it gets into equipment. It's a problem for current Mars rovers. During terraforming, the dust would interact with the developing atmosphere. Wind patterns would change. Dust storms might become less intense as the atmosphere thickens. Water would bind the dust. Organic matter would accumulate. Over time, the red dust would become less of an issue. Vegetation would cover it. Soil would develop. Mars would go from a dusty desert to a world with soil and vegetation, like Earth. But during the transition, there would be storms. Atmospheric circulation would be complex. Dust would blow around in new patterns. Weather systems would develop. This would be dangerous for human settlements. Settlements would need to be designed to withstand dust storms. Equipment would need protection. But eventually, the dust would settle. The atmosphere would stabilize. Weather would become predictable. Let me talk about what happens to Mars's ice caps during warming. The polar ice caps are cold. They're at temperatures approaching absolute zero. As you warm the planet, they start to change. First, the temperature rises. The carbon dioxide ice on the South Pole starts to sublime directly into gas. Carbon dioxide enters the atmosphere. This adds to greenhouse warming. The water ice on the North Pole starts to melt. Liquid water appears. It flows downslope toward the low areas. Streams form. Eventually, lakes. The caps themselves shrink. They don't disappear entirely. Even in a warmed Mars, they might retain ice in the coldest areas. But they become much smaller. As they shrink, they reveal the surface beneath, rock that hasn't been exposed in billions of years. You might discover geological features, might find evidence of ancient life if it existed. The caps would gradually disappear from the South Pole entirely, assuming you warm Mars by 50 plus degrees Celsius. The North Pole would retain water ice at the top of mountains and in very cold areas. But most of it would melt. This is a process that would take hundreds or thousands of years. Gradual melting, streams forming, lakes appearing, eventually oceans in the low areas. Let me talk about settling patterns and infrastructure development on terraforming Mars. Early settlements would be in practical locations, near water ice deposits, near good landing sites, near mineral resources. As the planet warms, locations change in value. Areas that were icy become suitable for habitation. Low areas that would flood become less valuable. High areas become more valuable. Over centuries, settlement patterns would shift. Initial settlements might become abandoned as better locations become habitable. New cities would grow in ideal locations. By the time Mars is fully habitable, the settlement pattern would reflect centuries of development and relocation. Cities would cluster along coastlines where habitable. Inland areas would have farms and mining operations. Polar regions would have research stations. High mountains would have settlements. The actual urban development would be fascinating from an urban planning perspective. Cities designed from scratch. No need to work around existing infrastructure. Cities designed for Martian conditions but planning for habitability as conditions improve. You might see unique architecture, structures that work in low pressure, evolving into structures optimized for Earth-like pressure. Farms that start in domes, evolving into open fields. Over thousands of years of development, Mars would have a unique human infrastructure, not copies of Earth cities, but new designs, adapted to Mars, unique to Mars. Let me talk about the role of nuclear power in terraforming, because this would be crucial. Mars has no fossil fuels, no coal, oil, or natural gas to extract. To power factories and settlements, you need a power source. Solar power would work, but Mars is farther from the sun than Earth. Solar panels would be less efficient. They'd get dusty. You'd need massive arrays to generate significant power. Nuclear power is more practical. Nuclear reactors could provide reliable power for factories, for settlements, for processing minerals. You need to ship nuclear fuel to Mars or process fuel there. Both are doable. Nuclear power is proven technology. Smaller reactors suitable for Mars exist. Nuclear power would be essential for terraforming. The factories producing greenhouse gases would likely be powered by nuclear reactors. This raises some safety concerns, obviously. Nuclear facilities on Mars. But the engineering is feasible. Reactors can be shielded. Waste can be managed. Over time, as the biosphere develops, solar power might become more practical, more efficient panels, more light available as atmospheric clarity improves. Eventually, Mars might support large-scale solar farms. But initially, and during the active terraforming phase, nuclear power would likely dominate. Let me talk about using existing Martian minerals and resources as much as possible, rather than importing everything from Earth. This is economically important. Shipping everything to Mars from Earth is enormously expensive. You want to use Martian resources wherever possible. Mars has minerals, iron, sulfur, silicates. You could extract and process these. You could build equipment from Martian materials. You could manufacture things on Mars. Early Mars manufacturing would be limited, but as infrastructure develops, you'd build more of your equipment locally. This would reduce dependence on resupply from Earth. It would make Mars more self-sufficient. Eventually, Mars might export to Earth. Rare minerals, processed goods. A trade relationship would develop. This has important implications for long-term terraforming. Mars doesn't need to be a permanent colony dependent on Earth. It can become economically independent, able to sustain and expand itself. This is actually necessary for long-term terraforming success. A Mars that's dependent on Earth for resources can't sustain a multi-thousand-year terraforming project. A Mars that's self-sufficient can. Let me talk about the psychological challenges of living on a terraforming Mars. Imagine a human in the year 3000 AD. They're a Martian, born on Mars. Their entire life has been on a cold, dead world being slowly transformed. They experience slow climate change. The seasons might shift gradually. The weather might slowly become more temperate. The ice might gradually retreat. Oceans might slowly fill. These are incredibly slow changes, slow enough that people might not notice them from year to year. But over their lifetime, they'd notice. Over generations, the changes would be profound. This is psychologically significant. They're witnessing planetary transformation. They're part of something cosmic. It might inspire them, it might make them proud, but it might also be isolating. They're on a slowly changing alien world. Earth is a historical abstraction. They're not part of Earth culture. They're creating something new. This would create new cultures, new philosophies, Martian identity, separate from Earth. Over thousands of years, these cultural differences would deepen. Martians would see themselves as fundamentally different from Earthlings. This could be healthy. Expansion of human civilization to new worlds. Or it could create tension. Us versus them dynamics between planets. But either way, it's psychologically and sociologically profound. Let me talk about what motivates terraforming beyond just having more habitable space, because there's something deeper here. Humans have always explored, always expanded, always tried to go to new places. It's been a fundamental part of human nature for thousands of years. Terraforming extends this impulse to planets. It's exploration and expansion on a cosmic scale. It's answering the question, can we create new worlds? Can we spread life beyond Earth? For some people, this is inspiring. It represents human potential, our ability to dream big and achieve extraordinary things. For others, it's concerning. They worry about the ethics. They worry we'll repeat Earth's mistakes on other worlds. They worry about the resources required. Both perspectives are valid. Terraforming is genuinely ambitious and worth carefully considering. But I think there's a case to be made that terraforming, done carefully and thoughtfully, could be positive. It could expand life. It could inspire humanity. It could demonstrate that we can undertake projects of cosmic significance. Let me end with a thought about what terraforming represents for human civilization. If we terraform Mars, it says we believe in ourselves. We believe humanity is worth expanding. We believe our civilization will last thousands of years. We believe we're capable of transforming worlds. These are bold claims, but they might be true. Terraforming might be the defining project of our civilization, the thing we're remembered for, the thing that proves we were capable of more than we thought. Or we might never terraform. We might stay on Earth. We might never try to transform other worlds. Both are possible. Both are legitimate choices. But the fact that we can conceive of terraforming, that we can imagine transforming planets, that we can calculate how to do it, that tells us something profound about ourselves. We're a species that dreams big, that reaches for the stars, that wants to expand and create and transform. Whether we actually terraform Mars or Venus or Europa remains to be seen. But we can. That's the important part. We have the theoretical knowledge. The engineering is feasible. The timeline is long but manageable. It's up to future generations to decide whether to pursue it. Let me talk in more detail about asteroid mining and water importation for terraforming, because this could be crucial to Mars's habitability. Mars needs water. The question is how much is already there and how much we'd need to import. If Mars has 10 to 20 meters of water depth equivalent on average, that's still enormous. But if we want Earth-like oceans covering 70% of the planet with an average depth of 4 kilometers, we'd need far more. Water-rich asteroids exist in the asteroid belt between Mars and Jupiter. These asteroids contain water ice and hydrated minerals. Calculating which ones contain the most water and identifying their orbits is challenging but doable. The process would be 1. Identify promising water-rich asteroids using spectroscopy and orbital calculations. 2. Send spacecraft to nudge the asteroids into Mars-crossing orbits. 3. Calculate trajectories to land them on Mars, not destroy the planet. 4. Deploy automated systems to monitor and adjust trajectories. 5. Manage impacts to avoid catastrophic damage. 6. Extract water from impact sites and manage resulting atmospheric changes. This could happen over centuries. Import in dozens or hundreds of large asteroids. Each impact adds water. Each impact adds energy, heat. Each impact adds organic compounds and minerals. The engineering is challenging. You'd need propulsion systems. You'd need precise calculations. You'd need to account for Mars's gravity affecting the asteroids differently than expected, but it's doable. The advantage is that asteroid impacts would solve multiple problems simultaneously: adding water, adding heat, adding organic material. The disadvantage is the dramatic nature of impacts. They'd reshape the landscape. They'd create geological upheaval. But spread out over centuries, the impacts could be managed. You'd target specific regions. You'd plan the sequence to achieve terraforming goals. This is actually an exciting part of terraforming to contemplate: deliberately crashing asteroids into a planet as part of a long-term engineering project. It's dramatic and audacious. Let me talk about what happens chemically as Mars warms and develops an atmosphere. As temperature increases, chemical reactions accelerate. Water ice melts. Carbon dioxide sublimes. Minerals in the soil release trapped gases. These gases accumulate in the atmosphere. Perchlorates in the Martian soil would react with warmth and moisture. They'd break down. This could produce chlorine compounds that would add to the greenhouse effect. Iron oxides in the rust-colored soil would remain relatively stable, but the water would enable different chemical weathering patterns. New compounds would form. Over thousands of years, the chemistry of Mars would shift dramatically. Not just the atmosphere, but the soil chemistry, the surface chemistry, the subsurface chemistry. Mars would become chemically different. This is important because it affects what plants can grow. It affects what organisms can survive. It affects the entire trajectory of biological development. Early terraformers would need to monitor soil chemistry, understand what's happening, potentially modify the chemistry deliberately to create better conditions for life. This connects to the biological side of terraforming. You're not just changing the physical planet, temperature, pressure, atmospheric composition. You're changing the entire chemical environment, creating conditions where Earth life can actually thrive. Let me talk about the role of micrometeorites and cosmic dust during terraforming. Mars experiences constant bombardment from cosmic dust and small meteorites. This dust would interact with the developing atmosphere. Some dust would burn up in the upper atmosphere, creating meteors. Some would settle as sediment. Over thousands of years, cosmic dust accumulation would add material to Mars. This sounds minor, but over millennia, it's significant. You might add meters of material from cosmic dust alone, More importantly, meteorite impacts would stir up the regolith. They'd mix materials, they'd create heat. Small impacts would be constant throughout the terraforming process. This is actually useful. The stirring helps distribute organic matter. The heat helps chemical reactions. The constant small impacts contribute to atmospheric warming. So cosmic bombardment, which is normally a problem for life, becomes part of the terraforming mechanism. Let me talk about ocean formation and how it would progress on terraforming Mars. Initially, water from melting ice caps would flow into low areas. It would pool. Small lakes would form. As more water accumulated, lakes would merge. Rivers would develop. Large bodies of water would form in the major basins. Eventually, the northern plain would flood, creating a northern ocean. The Hellas Planitia basin would fill with water. Various other low areas would become seas and lakes. The ocean would not be like Earth's ocean immediately. It would be cold. The water would contain dissolved minerals from Martian rock. The salinity might be different. The chemistry would be Martian, at least initially, but over time, processes would normalize it. Biological processes would affect the chemistry. Atmospheric circulation would distribute water. Evaporation and precipitation would create a water cycle. Eventually, the Martian oceans would develop currents. Weather systems would develop. Tides would exist, though smaller than Earth's due to Mars's smaller moons. The ocean would become a proper planetary water system, similar to Earth's oceans but Martian in nature. Life would colonize the oceans. Microbes first, then gradually more complex organisms. Eventually, fish and marine ecosystems might develop. This is thousands of years in the future, but it's the trajectory from melting ice to life-filled oceans. Let me talk about the role of extremophiles in early terraforming. Extremophiles are organisms that thrive in extreme conditions. Thermophiles that survive boiling water. Psychrophiles that survive near absolute zero. Halophiles that survive extreme salinity. Acidophiles that survive extremely acidic conditions. Early Mars, being harsh, would favor extremophiles. Organisms introduced to Mars would need to be extremophiles to survive, but extremophiles would gradually spread and diversify. As conditions improved, more organism types could survive. Non-extremophiles could be introduced. The biological diversity would increase. This is how Earth's biosphere developed. Early life was mostly extremophiles. As Earth's conditions became more moderate from a very harsh early state, more organisms could survive. Life diversified. Terraforming Mars would follow a similar pattern. Start with extremophiles. Let them transform the environment. Then introduce less hardy organisms. Let the ecosystem develop complexity over thousands of years. This is actually efficient. You're letting life do the work, adapted to conditions that exist, rather than trying to perfectly maintain Earth conditions while introducing Earth organisms. Let me talk about the role of lichens in Mars terraforming. Lichens are symbiotic organisms, fungi and algae living together. They can survive incredible conditions. They can break down rock. They can tolerate radiation. They're incredibly hardy. Lichens would be perfect for early Mars terraforming. Introduce them early, when Mars is still harsh. They'd survive. They'd break down rock, creating soil. They'd produce oxygen as a byproduct of photosynthesis. Over centuries, lichens would spread across Mars. They'd be the vanguard of the terraforming biosphere. By the time Mars became warm enough for more complex plants, the lichens would have already begun building soil. This would actually accelerate the process. Rather than waiting for conditions to become perfect for complex plants, you're introducing organisms that improve conditions, which then allows more complex organisms. It's a layered approach. Extremophile bacteria first, then lichens, then mosses, then grasses and shrubs, then trees. Each layer modifies the environment for the next. Let me talk about the psychological perspective of Martians, humans born and raised on Mars, as the planet transforms. Consider a child born on Mars in year 2800 during early terraforming. They grow up in habitats. Mars is harsh and cold. The sky is butterscotch. The soil is red dust. There's no liquid water on the surface. By the time they're old, in year 2900, the transformation is noticeable. The atmosphere is slightly thicker. Temperatures are noticeably higher. There are small ponds and lakes. Vegetation is spreading. The sky is slightly more blue than butterscotch. Over their lifetime, they witness this transformation. They're living through planetary change. It's profound psychologically. Their children, born in year 2900, experience Mars differently. To them, the ponds are normal. The vegetation is normal. They see further transformation during their lifetimes. By year 3800, 20 generations later, Mars is radically different. Blue oceans, vegetation-covered continents, breathable atmosphere with oxygen supplements. Weather systems. A person from year 2800 would barely recognize it. A person from year 3800 would consider it normal. They'd be a fully Martian human in a fully Martian world. This generational progression would create cultural evolution. The old stories from the harsh early Mars would become mythology. The values and knowledge developed on terraforming Mars would shape culture. Over thousands of years, Martian culture would become distinct from Earth culture. Different art, music, literature, philosophy. Different values shaped by the experience of living on a transforming world. This is one of the most fascinating aspects of terraforming. We're not just creating a habitable world, we're creating the conditions for a new branch of human civilization, a new culture, a new way of being human. Let me talk about potential resources and economic opportunities on terraformed Mars. Once Mars is habitable, it becomes valuable. Real estate, farmland, mineral extraction, though easier when the planet isn't hostile. Agriculture would be major, growing food on Mars for Martian populations and potentially exporting to Earth. Minerals. Mars has vast mineral deposits, iron, sulfur, rare earths. Once the planet is stable and habitable, mining becomes practical. You could extract and process minerals for use on Mars or export to Earth. Manufacturing. Lower gravity on Mars makes some manufacturing more efficient. You could manufacture things designed for space and export them. Tourism. A terraformed Mars would be incredibly attractive to tourists. Walking on an alien world that's now habitable, seeing ancient Martian geology, experiencing a different planet, research and development. A second habitable world is invaluable for scientific research. Study life's adaptability. Study planetary geology. Study the effects of lower gravity on biology and physics. These economic opportunities would drive interest in terraforming. What seems like an enormous expense upfront becomes an investment that pays off over centuries. Eventually, a terraformed Mars could be economically comparable to Earth regions, supporting billions of people, generating wealth, contributing to human civilization. Let me talk about the role of science and continuous learning during terraforming. Terraforming is ultimately an enormous scientific experiment. You're watching a planet transform, monitoring every aspect, learning what works and what doesn't. This creates opportunities for discovery. You might discover new chemical reactions occurring at planetary scale, unexpected interactions between biological and physical systems, new insights into planetary dynamics, new understanding of life's adaptability, new technologies developed to solve terraforming challenges. All of these discoveries would benefit science generally: earth science, physics, astrobiology, geology. Scientists would flock to Mars to study the transformation. Research stations would proliferate. The scientific understanding of planets would increase dramatically. This is actually one of the strongest arguments for terraforming. Even if it took resources and effort, the scientific knowledge gained would be invaluable. We'd understand planetary systems far better. Let me talk about potential risks and how they'd be managed during terraforming. Risk: equipment failure during critical phases. Management: redundancy, multiple systems, backup equipment, regular maintenance. Risk: unexpected atmospheric or chemical changes. Management: continuous monitoring, rapid response capabilities, flexibility in terraforming methods. Risk: biological adaptation creating problems. Management: quarantine systems, monitoring introduced organisms, ability to remove organisms if necessary. Risk: asteroid impacts causing more damage than expected. Management: careful trajectory calculations. Impact zone management: small test impacts before major ones. Risk: loss of commitment by human civilization. Management: build culture that values terraforming, ensure institutional persistence, develop AI to continue work if needed. None of these risks are unmanageable. They're challenges requiring careful planning and monitoring, but terraforming would proceed despite them. The key is accepting that some things will go wrong, planning for that, and maintaining flexibility to adapt. Let me talk about the final stages of terraforming when Mars is nearly complete. After 8,000 years of terraforming, Mars is nearly habitable. The atmosphere is mostly nitrogen and oxygen, like Earth. The pressure is similar to Earth. The temperature is moderate. Oceans exist. Continents are green. But it's not complete. There are still differences from Earth. The gravity is still lower. Life would need to adapt to this, or humans need to accept the difference. The day is slightly longer, 24 hours and 37 minutes instead of 24 hours. Organisms would adapt to this. The weather is different. The radiation is lower than early Mars, but higher than Earth due to the thinner magnetosphere. This would continue to be managed with atmospheric protection and possibly an artificial magnetic field. The oceans would have different salt composition than Earth, different pH, different biological balance, but it would be recognizable as a habitable world. You could live on the surface without a spacesuit. You could grow Earth crops or adapted versions. You could exist in the open. The final stages of terraforming would focus on perfecting these last details, creating ecosystems more similar to Earth's, adjusting atmospheric composition, building a more robust biosphere. These final stages might take thousands of additional years. Getting Mars from barely habitable to Earth-like is harder than getting it from airless to barely habitable. But eventually it would be done. Mars would be a world where humans lived naturally, where children played in parks, where crops grew in fields, where civilization developed. This is the ultimate goal of terraforming. Not just making Mars habitable, making it genuinely Earth-like, making it a real home for humanity. Let me talk about what we'd learn about life and biology from terraforming Mars. Terraforming would give us unprecedented insight into life's flexibility. We'd watch organisms adapt to Martian conditions. We'd see how life spreads across a new world. We'd understand the requirements for biosphere development. Early terraformers would observe extremophile bacteria thriving on harsh Mars, then surviving as conditions improved, then being joined by less hardy organisms. Over thousands of years, we'd see life adapt and evolve. This would teach us about evolution. We could study how organisms respond to environmental changes. We could measure adaptation rates. We could understand natural selection in action. We'd also learn about ecology, how ecosystems develop, how species interact, how balance is achieved, what creates stability, what creates collapse. This knowledge would be invaluable for Earth conservation. Understanding how ecosystems work on Mars would help us understand and restore Earth ecosystems. We might discover that life's adaptability is greater than we thought. Organisms might thrive in Martian conditions despite our predictions that they couldn't. This would expand our understanding of what life is capable of. Conversely, we might discover that some organisms we expected to thrive actually failed. This would also teach us something valuable. The entire terrestrial biosphere would be present on Mars, creating a living laboratory for biology. Let me talk about the role of insects and invertebrates in Martian terraforming. Insects are crucial to Earth's ecosystems. They pollinate plants. They decompose organic matter. They control pests. They're part of food chains. On terraformed Mars, insects would play similar roles, but there would be a lag. Early in terraforming, when there's still sparse vegetation, there would be few insects. As vegetation expanded, introducing insects would become important, but you'd need to introduce them carefully. The wrong insects could become pests. You'd need pollinating insects to go with flowering plants. Insects would be introduced in waves, beetles and ants first, because they can survive harsh conditions. Then bees and flying insects as flowers became common. Then predatory insects to control populations. Over thousands of years, Martian insects would adapt to Martian conditions. They'd evolve. They'd potentially diverge from Earth insects, becoming distinctly Martian species. This would create unique ecosystems, Martian insects pollinating Martian plants, adapted to Martian gravity and atmospheric conditions, creating a food web unique to Mars. The role of insects might be underappreciated in terraforming discussions, but they'd be essential to creating a functional biosphere. Let me talk about how terraforming Mars would be governed and managed. Terraforming requires coordination across centuries, consistent policies, institutional structures that persist. Early terraforming might be managed by Earth governments or international bodies. Later, Martian governance would take over, self-governance by Mars's population. Policies would need to address how much to accelerate terraforming, what organisms to introduce and when, how to manage resources, how to handle conflicts between terraforming goals and other priorities, how to preserve scientific study areas, how to manage economic development. These policies would need to be flexible, responding to unexpected developments, adjusting to new information. Governance structures would need to outlast generations. Institutions would need to train successors. Knowledge would need to pass down. This is actually one of the biggest challenges of terraforming. Not the technology, but maintaining the commitment and coordination for thousands of years. It would require creating governmental structures and institutions that can persist across millennia. This is actually harder than the engineering. Let me talk about the role of artificial intelligence in long-term governance and management. By the time terraforming begins in earnest, AI systems will likely be far more advanced than current systems. These AIs could play crucial roles in management. Is could monitor terraforming progress constantly, adjust systems, optimize processes, run calculations, manage infrastructure. AIs could enforce policies consistent over centuries. They don't have personal interests that change. They don't pursue power or wealth. They can maintain goals across generations. This creates an opportunity. Use AIs to maintain terraforming direction and commitments across millennia, while human governance handles policy decisions and adaptation. Humans would decide what terraforming goals to pursue. AIs would execute those goals consistently. Humans would adjust goals based on results. AIs would adjust execution accordingly. This partnership, human judgment with AI execution, could make long-term terraforming projects actually feasible. The risk is that AIs might pursue goals in ways humans didn't anticipate, or that AIs might make decisions humans would object to. This requires careful design of AI systems and their constraints. But potentially, AI is the enabling technology for terraforming. It solves the continuity problem. Let me talk about potential future modifications to Martian life. As terraforming progresses, humans would have ability to modify organisms more dramatically. Genetic engineering would be more advanced. Rather than just importing Earth life and hoping it adapts, humans could engineer life specifically for Mars. Plants engineered to thrive in Martian gravity, trees engineered for Martian light levels, crops engineered for Martian soil, microbes engineered to process Martian minerals more efficiently, insects engineered for Martian atmospheric composition, animals engineered for Mars, livestock adapted to lower gravity, wild animals designed for Martian ecosystems. This raises ethical questions. Is it right to engineer life for other worlds? Does life have intrinsic value that shouldn't be altered? But pragmatically, engineered organisms might be necessary for successful terraforming. Earth organisms adapted for Earth conditions might not thrive without genetic modification. Future Martians might see engineering life for Mars as ethical and necessary. The alternative, not terraforming, might seem worse to them. This is a decision for future generations. But the capability to engineer Martian life would exist. Let me talk about what happens if terraforming Mars fails or is abandoned. Terraforming is a long-term commitment. What if humanity loses interest? What if we encounter insurmountable problems? What if resources dry up? If terraforming was abandoned halfway through, Mars would remain partially transformed. Some changes would persist. Greenhouse gases released would continue to warm the planet for centuries. Introduced organisms would persist if they adapted. Mars might end up in an unstable state, neither fully terraformed nor fully Martian. Some areas habitable, others not. Strange hybrid ecosystems. Eventually, Mars might stabilize at some intermediate state, not fully living, but not fully dead either. This wouldn't be catastrophic. Mars wouldn't collapse into some terrible state. Life that took root would continue. The planet would just not reach full Earth-like habitability. But it would be a missed opportunity. Humanity would have committed enormous resources to a partial project. Future generations would either continue terraforming or accept Mars as an intermediate world. This actually argues for thinking carefully about whether to begin terraforming. Once you start, you're committing to completion. Abandoning it halfway wastes resources and leaves Mars in an awkward state. Let me talk about how terraforming Mars could inspire broader human ambitions. Successfully terraforming Mars wouldn't be the end of human expansion. It would be the beginning. With Mars terraformed, Venus becomes more feasible. We'd understand the process better. We'd have technology proven on Mars. We'd have the confidence and resources. Europa and other moons would become targets, terraforming moons to create habitable worlds for humans. Eventually, planets around other stars might be terraformed. This would require centuries or millennia to reach those worlds, but the goal would exist. Terraforming Mars, in this view, is the first step in expanding human civilization throughout the solar system, then eventually to other star systems. It would represent a fundamental shift in human identity, no longer confined to Earth, spread across multiple worlds. A spacefaring civilization. This is incredibly ambitious. But it starts with Mars, one world at a time. Let me talk about the philosophical implications of terraforming. Terraforming raises profound questions about human purpose and responsibility. Do we have the right to transform other worlds? What are our obligations to preserve nature? What is our role in the universe? Different philosophical traditions would answer differently. Some would argue that spreading life and consciousness is inherently good, that expanding the biosphere serves a cosmic purpose, that humans have a role as gardeners of worlds. Others would argue that we should preserve natural worlds. That taking Mars as it naturally is has value, that we shouldn't impose our vision on other worlds. Still others would argue pragmatically. Terraforming Mars helps humanity survive. It provides insurance against extinction. It gives purpose to human civilization. All these perspectives are valid. Different people will reach different conclusions. But I think terraforming forces us to confront fundamental questions about what we value, what kind of civilization we want to be, what kind of legacy we want to leave. These are questions worth spending time on, even if we ultimately decide terraforming is wrong. Let me wrap up by talking about why terraforming matters beyond the practical considerations. Terraforming represents human aspiration. It's saying we can dream big. We can imagine transforming entire worlds. We can work toward goals that take millennia. It's saying we believe in humanity's future. We believe we'll be around for thousands or millions of years. We believe we're worth the effort to expand beyond Earth. It's saying we're curious. We want to understand other worlds. We want to experience other places. We want to expand our consciousness through exploration. It's saying we're creative. We can imagine things that don't exist. We can work to bring them into being. We can create new worlds. Whether we actually terraform Mars is less important than the fact that we can conceive of it, calculate how to do it, and seriously consider pursuing it. Terraforming is a window into who we are as a species. It shows our ambition, our creativity, our willingness to take on enormous challenges. And if we actually achieve it, if we actually terraform Mars, if we actually transform a dead planet into a living world, that would be one of the greatest achievements in human history. It would prove that consciousness can reshape worlds, that humans are capable of extraordinary things, that we can take on projects of cosmic significance. It would inspire future generations to dream bigger, to work on problems that seem impossible, to believe that anything is achievable with enough commitment and resources. In that sense, terraforming matters not just as a practical goal, but as an inspiration, a demonstration of what humanity is capable of. Maybe we won't terraform Mars. Maybe we'll stay on Earth. Maybe we'll focus on other challenges. But the fact that we can imagine it, that we can figure out how to do it, that we can seriously contemplate transforming another world, that tells us something profound about ourselves. We're a species that reaches for the stars, that tries to achieve the impossible, that dreams big and works to make dreams real. That's the most human thing about us. Let me discuss one final aspect: how terraforming connects to our search for meaning. Throughout human history, exploration has been central to how we find meaning. Discovering new lands, climbing mountains, diving to ocean depths, walking on the moon. Terraforming is exploration on a completely new level. It's not just discovering new worlds, it's creating them. It's taking an entire planet and transforming it into something new. There's something profound about that. We're not just passive observers of the universe, we're active participants. We're reshaping it according to our will and vision. Some find this empowering, others find it troubling. But it's undeniably meaningful. Working on a terraforming project that spans millennia would give enormous meaning to human civilization. It would be the project that defines us, the thing we're remembered for, the thing that shows we mattered on a cosmic scale. Individual humans working on terraforming would have purpose beyond their personal lives. They'd be part of something vast, something cosmic, something that would outlast them and their great-great-grandchildren. That's meaningful. That's worth dedicating to. This might be why terraforming captivates us. It's not just about creating more habitable real estate. It's about finding meaning, purpose, a reason to believe humanity matters. Let me also talk about how terraforming relates to our understanding of time and progress. Humans naturally think in short timescales: years, decades, maybe centuries. Longer than that, and it becomes abstract. But terraforming requires thinking in millennia, thousands of years, timescales that dwarf human lifespans. This actually changes how we think about progress. On an annual basis, terraforming Mars seems impossibly slow. On a millennial basis, it's rapid. It teaches us humility about our place in time. We're tiny moments in vast stretches of history. But our actions can have consequences lasting thousands of years. It also teaches us patience. Progress isn't always visible day to day, but over generations, mountains can be moved. Worlds can be transformed. This perspective could actually help us on Earth. Understanding that massive changes take time, that we need to commit to long-term projects, that short-term setbacks don't mean failure. Terraforming teaches us to think bigger, to make plans with longer timescales, to commit to goals that benefit future generations. That's valuable, whether or not we ever actually terraform Mars. Let me talk about how to communicate terraforming ideas to future generations. If terraforming is going to succeed, future generations need to understand it, support it, continue the work. This requires more than just explaining the physics and engineering. It requires inspiring people, making them understand why this project matters. It requires stories, narratives, visions of what a terraformed Mars would be like, what it would mean for humanity. It requires teaching the philosophical foundations, why we think terraforming is right, what values it represents. It requires maintaining knowledge, ensuring that information about terraforming isn't lost, that future generations can access the accumulated understanding. This might mean creating institutions specifically to preserve terraforming knowledge and maintain commitment to the project. It might mean creating art, literature, and music celebrating terraforming, making it culturally significant so people want to continue it. It might mean rituals and celebrations marking terraforming milestones, creating traditions that carry the project forward. This cultural and institutional dimension is actually as important as the technological dimension. You can have perfect engineering, but if you lose the will to terraform, the project dies. Let me talk about analogies to historical projects that lasted centuries. Cathedral building in medieval Europe lasted for centuries. Individual builders worked on projects they wouldn't see completed. Generations of workers continued construction. The project persisted through wars, economic crises, changing rulers. Yet the cathedrals were built. Most took 100 to 300 years. The investment was enormous for the time, but they saw the cathedrals through. Great walls, aqueducts, irrigation systems, projects that took centuries and required coordination across generations. These projects are inspiring because they show that humans can commit to long-term projects, can maintain knowledge across generations, can work toward goals that take longer than a human lifetime. Terraforming would be similar, but on a much longer time scale. Instead of 200 years, we're talking about 5,000 to 10,000 years. But the principle is the same. If we did it before, we can do it again. On a bigger scale, on a longer time scale, transforming entire worlds instead of building cathedrals. This gives me confidence that terraforming is actually possible, not just technically, but as a human endeavor. We've shown we can do long-term projects. Terraforming is just a bigger version of what we've already done. Let me make one final observation about terraforming and human civilization. Terraforming might not happen in the way I've described. The timescales might be different. The methods might be different. The outcome might be different. We might terraform Mars partially instead of completely. We might create habitats instead of full terraforming. We might discover that full terraforming is infeasible and settle for something less. Or we might develop technologies that make terraforming far easier and faster than current calculations suggest. We might terraform Mars completely and then move on to other worlds. The actual future might diverge significantly from what I've described, but the key point remains. Terraforming is possible. The physics works. The engineering is challenging, but not impossible. The timescales are long, but manageable. Whether we actually do it depends on choices we make, on what we value, on what kind of civilization we want to be. That's both inspiring and sobering. We have the power to transform worlds. The question is whether we have the wisdom to use that power well. That's a question for our descendants to answer. All we can do is understand the possibilities, understand what we're capable of, and make the best choices we can with that knowledge. The universe is vast. Most of it is empty space and lifeless rock. But on this one small world, life emerged. Consciousness emerged. Humans emerged with the capacity to understand the universe and transform it. That's extraordinary. That's worth contemplating. Whether we terraform Mars or not, the fact that we can conceive of it, understand how to do it, and debate whether we should do it, that's what makes us human. We dream big. We reach for impossible things. We try to transform worlds. That's beautiful. That's worth celebrating. Let me make one final point about the state of terraforming science today. Right now, in 2026, we don't have active terraforming projects on Mars. We have small robotic rovers exploring the surface. We're planning the first human missions for the coming decades. But terraforming research exists. Scientists have published peer-reviewed papers on terraforming methods. Engineers have designed systems. Biologists have considered which organisms would work. It's not active projects, but it's serious thought, serious science, serious engineering. This gives me confidence that terraforming isn't fantasy. It's plausible, it's grounded in real science and engineering. The obstacles are real, the timescales are long, the challenges are enormous, but they're not insurmountable. If human civilization commits to it, if we dedicate resources and maintain commitment across millennia, we could terraform Mars. We could create a second habitable world. That's an inspiring thought. Not something to do immediately, not something we must do, but something we could do if we chose to. And having that knowledge, that possibility, that option, it changes how we see ourselves. We're not limited to Earth. We could expand. We could grow. We could transform other worlds. We're a species capable of shaping planets. That's profound. What we do with that capability is up to us. Do we terraform Mars? Do we preserve it in its natural state? Do we find a middle ground with partial transformation? These questions are for future generations to answer. For now, it's enough to understand that we have the knowledge and capability. It's enough to understand what's possible. Understanding possibilities expands our imagination. It makes us think bigger. It makes us believe that ambitious goals are achievable. That's the value of understanding terraforming, even if we never actually do it. We understand that our descendants have options, that human civilization could expand across the solar system, that we could create new worlds, that we could spread life and consciousness beyond Earth. These possibilities inspire us. They make us believe that human civilization has a future, that we matter on a cosmic scale, that we're capable of extraordinary things. Whether we actually terraform Mars is less important than knowing that we could, knowing that we have the knowledge and capability makes us see ourselves differently. We're not limited to what we have. We're capable of transformation. We're capable of creating worlds. That's what it means to be human at this moment in history. We're at the threshold where we understand how to transform planets. We have the knowledge, we have the capability. We just need the will and the resources and the commitment across generations. Maybe we'll do it. Maybe we won't. But the possibility exists. And that possibility, that knowledge that we could transform another world changes everything about how we understand ourselves and our civilization. Let me talk about the legacy of a terraformed world. Imagine standing on Mars in the year 12,000. The planet is habitable. The atmosphere is breathable, maybe with oxygen supplements. There are oceans. There are continents with vegetation. There are cities and farms and cities and human civilization thriving. A Martian child could look at the night sky and see Earth as a blue dot. A historical curiosity, a legend where humanity came from. They'd know the history, they'd learn in school about the terraforming, about the ancestors who committed to transforming a dead world into a living one. They'd understand that they lived on a world their ancestors created, not discovered, but created, built, transformed through deliberate effort across thousands of years. That's a profound legacy. That knowledge that their world was created by human will and effort, that consciousness shaped the planet. The Martians would have stories about terraforming, myths and legends, historical narratives, celebrations of the terraformers. They'd understand that they inherited a project, that their ancestors dedicated millennia to giving them a home, that they have a responsibility to maintain and develop that inheritance. This creates meaning, purpose, connection to history. It's different from Earth, where we evolved naturally. On terraformed Mars, every biotic system, every atmospheric component, every ocean is there because humans put it there. Well, that connection between human intention and the living world would be central to Martian culture. There would be monuments to the first terraformers, research stations preserving artifacts from early terraforming, museums explaining the process. Young Martians would dream about the early days, about ancestors willing to work for thousands of years to make the world habitable, about the audacity of transforming an entire planet. This creates inspiration. It shows what humans are capable of, what commitment and vision can achieve. A terraformed Mars would be, in a real sense, a monument to human ambition, a testament to what we're capable of when we commit to a goal. Every tree on Mars would represent human intention. Every ocean would represent millennia of effort. Every breath of air would be thanks to ancestors' commitment. That's beautiful. That's a legacy worth creating. And for Earth, too, terraforming would matter. Knowing that we terraformed Mars would change how we see ourselves. It would prove that we're capable of transforming worlds. It would inspire us to tackle Earth's problems. If we can terraform Mars, we can restore Earth's ecosystems. If we can commit to terraforming Mars across millennia, we can commit to maintaining Earth for that long. Terraforming Mars would inspire us to be better stewards of Earth. It would also provide hope, a sense that if things go wrong on Earth, we have a backup. Humanity wouldn't be confined to one world. That's practical hope grounded in real capability. So terraforming Mars would matter not just for Mars, but for Earth too. It would change how we see ourselves and our civilization. And that might be the most important thing about terraforming. Not the literal creation of a habitable world, but the shift in consciousness it represents. The understanding that we're capable of cosmic scale projects, that we can shape worlds, that we can undertake ambitions that dwarf individual human lifetimes. That knowledge, that capability, that vision, that's what terraforming gives us. Whether we actually do it or not, understanding that we could do it changes us. We understand that our civilization has potential. We're not limited to Earth. We could expand, we could grow, we could create new worlds. That's the future. That's what's possible. So, what have we learned in this exploration of terraforming? First, we've learned that terraforming is scientifically and engineering feasible. The physics works, the methods exist. We understand how to transform Mars into a habitable world. It would take centuries or millennia, but it's possible. Second, we've learned that terraforming requires enormous commitment, thousands of years of sustained effort, institutional structures that persist across generations, AI systems that maintain goals, human will that doesn't waver. Third, we've learned that terraforming raises profound ethical questions. Should we transform other worlds? Should we preserve them in their natural state? What are our responsibilities? These questions don't have simple answers. Fourth, we've learned that terraforming would inspire human civilization. It would show us what we're capable of. It would prove that consciousness can shape worlds. It would inspire future projects and ambitions. Fifth, we've learned that terraforming is connected to understanding ourselves. It reveals what we value, what we dream about, what kind of civilization we want to be. Finally, we've learned that whether we terraform Mars or not, the possibility exists. We have the knowledge, we have the capability. We just need to decide if we have the will. That decision isn't ours to make alone. It's a decision for future generations. We can understand what's possible. We can share that knowledge, but our descendants will decide what to actually do. I believe they should know what they're capable of. They should understand that terraforming is possible. They should know that they could create new worlds if they wanted to. With that knowledge, they can make their own choices about whether to terraform, about how to terraform, about what kind of future they want. And whatever they choose, they'll do it with eyes open, knowing what's possible, understanding the implications, making conscious decisions about humanity's future. That's the most important thing. Having knowledge, having options, making deliberate choices about our destiny. Terraforming represents one possible future, not the only future, not necessarily the best future, but one that's possible, one that's worth understanding. And understanding it, we understand ourselves better. We understand our place in the universe. We understand what we're capable of. That understanding is valuable, whether or not we ever actually terraform Mars. The future is unwritten. The possibilities are vast.